Alright, so where did we leave off last time? We were talking about this idea of transformations. Okay, so we said that if you've got two coordinate systems like this, where one of them is moving v, a velocity v, with respect to the other, we can label this as s prime and s. And we came up with a way to go back and forth between all the coordinates. We can say that in x prime, we have x minus vt, and we have t prime is equal to t. Again, this is just classical physics, there's no time dilation or special relativity to be concerned about. And then the last one we said is u prime. U prime is equal to u minus v. Alright, so just a couple reminders. V is always left to denote the velocity between the respective reference frames. Okay? U is always the velocity of an object moving in the reference frames. So u refers to this object in this reference frame moving like this. So that's u prime, the velocity is moving in this reference frame. And of course, we'll assign some u in this other reference frame. Okay. Now, things to also mention that we didn't really cover. Y prime is equal to y, and z prime is equal to z. Anytime you have coordinates that aren't moving, that you're not changing with respect to motion, they're just going to be the same. There's no change in those. So that's nice and handy. We only have to worry about the ones that are where we're moving. So these are all known as classical transformation equations. Now you guys might remember something similar to this. This is transforming between two reference frames for movement. But we also have transformation equations when we're talking about moving from coordinate systems. Remember when we want to go spherical to Cartesian, or we want to go to cylindrical coordinates, we came up with a transfer set of equations to move from one to the other. So what's our goal today? To do the same thing, but come up with a special relativity version of them so that we can solve some of these problems. Yeah, okay, so yonder. We'll leave that space open for the next set of equations. It's nice if you can work with me or not.
You know, there are advantages to having a class in here.
Since was a lot of fun.
I mean, we got stronger feedback.
Alright, we're making the thumbnail next. Okay, that's right. Alright, wait, what? What are the advantages to being in here?
We constantly got video most days.
Yeah, see, that might be good for you. To me, it's unnerving. I don't be recording. Yeah, I don't want to watch myself. I can just see, because inevitably I'll download these and I'll look at it a couple years later and I'm like, I didn't know what the hell I was talking about. Do that.
So we shouldn't be doing the same then.
Sure. Take it with a grain of salt. Anything that I say. Well, you got to keep in mind, this is kind of interesting. As professors, there's no training. It's not like secondary school where you go to school for 5 years to learn how to be a teacher. No, they just, you go to school long enough and like, okay, now you can teach. Says who? What qualifications do you have to teach? None. Oh, okay.
You have a fair
Sure, why not? Well, so, I mean, like this stuff, I mean, I've had this once in undergrad. That was the time that I had it. My field was not special relativity, so what makes me a qualified teacher? I don't know. I just read 3 books on it and hope for the best. But anyway, we're relying mostly on the book. We're assuming that he's right. And I'll insert little information that I know as we go. Okay, so, special relativity. What can we talk about in this? First, we always want to get back to the idea that the time, t prime is not always going to be equal to t. When is it? There's one time specifically that we say that the times overlap. When is that?
At the start.
At the start, which we're going to say is when the origins cross each other. Okay, so we're going to do this whole thing, what we can call one origin as it's coming by. So there is negative time. Negative time is a real thing now that we're in modern physics. It refers to any time that's behind this. Okay, so if we get to negative time, that's what it's referring to. And we will today. It's not this grand quantity or grand scheme important thing. We've just called this, if I call today now 0 seconds starting right now, then yesterday was obviously negative time. All right, so, but we can say t of 0 is equal to t prime of 0. Those those two things are true. And we can say all the positions are true, x0, x prime 0, those are all going to overlap. Okay, so other things that we want to do whenever we're making our transitions. A couple of rules. First, I want to say an object moving in a reference frame must be moving with constant velocity. Everything we're going to do today and even do this in class is going to be constant velocity. Things get interesting when you start to accelerate. Okay, so we have the whole, if you guys remember my the green side and the orange side of the equations, which I guess Kyle, you're probably the only one who would remember that. But anyway, so the point being is that we're going to have linear motion. We're going to have linear position. We're going to have a constant velocity. Now, the next thing. Okay, frames also move at constant v with respect to each other. That would completely hose everything up if we allowed the opportunity for one of the reference frame to be accelerating at 3 meters per second squared or something like that. That is beyond the scope of what we're going to be talking about. So that means that if we're moving at a constant velocity, what can I say about the net force on the object?
0.
Yeah, okay, so I hammered this into you guys last year. The net force is equal to 0. Oh, actually, Brad, you've had me for calculus 1. When you're not here, Kyle's the only one who actually had me for the intro physics. Yeah, they don't have me for calculus 2.
Yeah, I had you for 1, sort of.
Sort of. All right, so we can say that the net force on the object is 0. All of these rules we have to go with, and we'll see why here in a minute. Now, if all this is true, there's no external forces acting on the object, so that force is equal to 0. This object is moving with a constant velocity in here. Now, from this reference frame, what can we say about that object's position? Is it going to be linearly changing, quadratically? How do you know? I suppose it's a difficult question to ask because we're branching into special line thinking. What do we know? But equation-wise, what does it look like it's going to happen? Linear, nonlinear?
Linear.
Why?
Because I don't see any squares.
Well, moreover than that, yes, it is going to be linear, but this is moving at the constant velocity with this, and then this is moving at constant velocity within here. There are no net forces. And that net forces thing is important, because whenever we talk about forces or acceleration, we talk about this concept of push or pull. Nothing is pushing or pulling on the object, so it'd be really interesting, even in terms of relativity, if all of a sudden we had a quadratic change in position. Okay, that would be an ever-changing velocity. How can you have an ever-changing velocity if, do you see what I'm saying? The velocity between the two reference frames is constant, and the velocity of the object is constant. So everything we're going to be dealing with is linked. That's handy. That is really, really nice. So everything's simpler. Okay. All right. Now, if that's true, then we're going to start off with two simple equations. Special relativity, SR, abbreviation for anything I won't talk about here. First one is that x prime is going to be equal to u prime times t prime. Okay, fine. And the second is that x equals u t. So within their respective coordinate systems, if they're looking at this object, we're saying that it must be moving linear. That's all that's saying. Okay, we'll get back to these equations. All right, next. Okay, although we're saying that this is linear, the other thing that we are going to say is that we are going to allow things to happen at different times and different places. In other words, if Brad and I are looking at two events, we're saying, oh yes, I saw this fall off or something like this, but according to my watch, it fell off at this time. Okay, versus mine, I'm going to say it happened at this time. Or the time between two objects, or the length of an object. All of that can necessarily be different. Nevertheless, we're going to say that everything has to be linear. Okay, so the easiest way to think about this is, when we have this object going across here, I'm just going to add to this. Let's think about it, and every now and then it's beeping. We're just going to add a beep there. In other words, every single one of those beeps, as this object is moving within one reference frame, we call that an event. We need something to tie together these two coordinate systems. So that's what we're going to call an event. And we're going to be able to analyze what an event looks like in one and what it looks like in another. Apologize for that. I don't know much. What, that?
Yeah. I was just waiting for the rain. I'm gonna walk a quarter mile through the.
I didn't either. I actually went to the third floor and stole an umbrella. I have no idea whose that is. It was lost and found. I took it. Okay, so now if we want to move from one coordinate system to the other, if we can say that one of them is linear within one frame, one of them is linear to the other, then the transformation also has to be linear. What is the definition of a linear equation? What is the most basic form? We want to write it down.
Y equals mx plus b?
Yes, y equals mx plus b.
And now you're going to confuse us.
So, what?
And now you're going to confuse us, right?
Confused you? Okay, sure. Why not? Sounds like fun. So if we're going to do this, I'm talking about going from one coordinate system to the other. So I'm going to write this as x prime is equal to mx plus b, something like that. The idea is to go from one coordinate system to the other. Be able to define the x coordinate in the new coordinate system from the old one. Okay, so when we did this before, we just had x prime is equal to 1x minus bt. And that's where we got our equation that we see up there on the top. X prime is equal to x minus bt. That's how we define this. So our slope was equal to 1, and then it was just an offset of minus bt. And that's all the only difference that mattered. There was an offset that was changing as a function of time. All right, so we can write this slightly more generally to say that x prime is equal to ax plus bt. This is the most general way that we can possibly write this. Some sort of offset due to time. Okay, this is our plus c, our constant, and this is our slope as a function of x. Now, the equation can't be any more complicated than this. Anything more than this is nonlinear. The second we add some sort of another function of x, okay, it's going to combine and we'll end up with some sort of x squared. This is just a constant, so this is as complicated as it could possibly get. So now, since we're also saying time can change, we also need to have one for time outlook. Time is going to be equal to cx plus dz. So now we've got one for each of them. Now there's going to be a couple of places along the way that you have to buy in. You have to buy what I'm saying for it to follow. Does everyone understand why these linear equations, they have to be linear essentially? Okay, good. There's going to be another one of those steps here in a little while. So the question becomes is, what the heck is A, B, C, and D? Now, I'm going to very quickly show you what they are, but largely that's your first homework problem, is you're going to show in detail in very clean handwriting the algebra for A, B, C, and D.
I'll apologize in advance.
No, you're not bad. You were not the person I was addressing.
Okay, Alexis, who's from Nucleus addressing?
Probably. 3 special cases. No, Drew's yours is not so bad.
Okay,
Actually, this is a good point, though. As far as a group of class, you're all not that great. I mean, jeez.
Wait, what about her?
Actually, no, hers is fine.
Were you going to call me Anna?
I was. I've had your sister more recently than you in class. I don't remember your handwriting.
It's not great. That's
And yours
not
isn't
too
bad. No, his isn't bad. Yeah, yours is the only handwriting I don't really remember. Alright.
I know you were mine.
Special cases. Alright, we could solve these constants by looking at simple special cases. What do I mean by special cases? And when times when the object's not moving, or when the object's tied to an origin or something like that, that'll allow us to solve for these. And we're going to get really good at this because this is the same approach to solving anything in Schrodinger's equations when we get to quantum. You'll always have these extra variables and you got to figure out what they are. Alright, so the first one. First special case. Special case 1. Am I still on here? Yeah, I am. Good. Alright. Object fixed so what do I mean by that? In other words, I'm going to go over here and I'm going to tie this object right here. Ha! You were just stuck there at the origin, and you get to move with that origin. All right. So, what does that tell me? Brad, in terms of the x prime coordinate, what does this necessarily mean that the object's x prime coordinate is? Not a problem. All right, so we've got this object stuck at s prime. It is on this whole coordinate system is moving. So in terms of x prime, what can I say that the coordinate is?
Not entirely sure.
Any guesses?
Its position is moving with that is relative to x.
Yeah, Anna's got it right. It's 0. 0 meters. It is tied to 0.
I'm not going to participate. You keep calling me that.
I have to put Lee in front of it. Lee. Ben, you can't really yell at it. Alright, 0 meters. Now, the reason being is it's tied to the darn coordinates. This is not a function of time, position, does not matter anything else. It is just stuck there. It's always going to be that. So, we're going to have x, we've said, is equal to ut. Here's some function, and that's what it's going to change. But what is my u in this case? What can I say that the velocity of the object is from x's point of view in our s coordinate system? Well, okay, let me ask you this way. What is u prime equal to?
The velocity in s prime's reference.
Awesome. Which is going to be what for the object? If the object is tied to the origin from s prime, what is the point of view? In s prime, give me in words what's going on with the object.
It's not moving.
It's not moving. It's just tied at s prime. So what is my u prime going to be? 0. Okay. So, and even if we look over there, so u prime is going to be u minus v. So my answer will necessarily be u, I'm going to say, is equal to what?
U is equal to V.
U is equal to v. So we've got u prime equals u minus v. U prime is 0, so v is from over the other side, and they're equal to each other. So if I come back up here, I can say that this is equal to vt. Now let's think about that for a minute. X is equal to vt. Yeah, because all we're saying is that the object, since it's moving with the coordinate system, it's just moving with the velocity of whatever the coordinate system is. It doesn't have any extra component to that. Okay, this is going to help us. All right, so that's our first special case. Now, if that's the case, we can go over here and we can plug this in that x equals vt, okay, and that x prime is equal to 0 into right here. This becomes 0. This becomes vt, and we can solve for b. Okay, which is the first part of your homework assignment. That's a. And b, we can say, is going to be equal to a negative av. Ta-da! Show me later. Specifically, your homework assignment is not going to take you long. It should take you half an hour, maybe, something like that, maybe an hour. But I do recommend you do it before Thursday. It's not due till Tuesday. Your homework, you always have a week to do it. But it will help you stay up to date with whatever we're doing. Plus, anytime you try a homework assignment, if you do try it before the next time we meet, you can actually ask me questions about it. Otherwise, you won't have that.
So you just substitute x into where x was at, right?
Yeah, so if this is going to be my x, vt, so now that this is my first special case, take all this knowledge and throw it into these two equations. The idea is we're going to keep plugging stuff into these two equations right here to try and solve for these variables a, b, c, d. We're going to come up with a nice system of equations that doesn't involve random stupid variables like over there. Okay, so that's the first one. V is equal to negative av. You know, I'm going to put these, I'm going to run out of room over here. Write it up here. Yeah, I'm going to write ut and t prime is equal to 6 dt. Alright, so I'm just going to keep adding things over here with the pool of knowledge that we obtain. Alright, what's our second special case? Another interesting one. So we've got object fixed at s prime. The second one we can do is, why not? Object fixed at s. Same idea. Okay, so now instead of where we've got the ball there, we're going to say the ball's over here. Come on. And it's stuck there. So from, let's see if we can figure this out right now. So my x coordinate is going to be equal to what, Brad? 0, there we go. The x coordinate is going to be equal to 0. So, and my x, let's see, what are the other things that are going to be really easy to figure out? Well, x prime. X prime is going to be a little bit difficult. We don't know what that is. We know that it has to be u prime times t prime. So maybe one of the first things that we should figure out is what the heck is u prime going to be equal to? Yeah, sure. Good call.
With that camera, is there a way to like the tilt where the sensor is at where somebody here can use it and still?
Tried that, yeah. We tried it the first couple of days.
Got to put a viewer somewhere.
No, this is, looks like it's infrared, so if someone wants to install, you know, a set of mirrors or something to that effect, you probably get it done. No, I'm sure it's fine. Alright, so what is u prime going to be equal to? How do you know? Drew, you got this. Over there on the left side of the thing, we've got an equation for the classical transformation. To say u prime is going to be equal to u minus v. So, an object is fixed at s, what am I going to say u prime is equal to? Yeah, because u is equal to 0. That's the other thing we know. If x is equal to 0 here, u has to be equal to 0. So u is going to be equal to negative v. And over here we said that u is equal to positive v. This kind of makes sense. So if we're moving away from this, it's as though the object is moving in negative v direction from us the other way.
Well, that's supposed to be u prime.
Yes, thank you. U prime, which I could have just left up here. I don't know why I'm looking at 3 quarters. Alright. So, therefore, x is going to be equal to negative v t prime. Now, if we plug that into our equations, we're going to find out that if we plug that down into our time equation, we can say that d is equal to negative v over v. But the thing is, look at our very first one we figured out. If d is equal to negative v over v, what can I say that d is equal to in terms of a? Or we can even look at it right here.
So it's d is equal to a.
D is just straight up equal to a. They're synonymous. Negative v over v. So if we bring over the negative v over here, negative v over v is equal to a. We drag the negative sign with us. Alright. And that's good news, because whenever we try and do this, we want to try and pare these down as much as possible. We want to get rid of these. So by doing that, we've just straight away gotten rid of one. So now there's one thing we need, one more equation. What do we want that to be? And you probably notice a pattern here. What don't we have information about? Okay, what do we want it in terms of? A. A. Yeah, I was going to say this right here. So we want C somehow as a function of A, because then we put everything in A, and we've got everything in A. All right. The other thing we need to point out is these first two cases, we're not doing anything different when we've got the classical transformations over here. If we just kept going with this and put nothing special relativity in here, nothing special about it, these would fall out and give us our original set of equations anyways. And we would just run around in circles and done nothing. Nothing in here is relativistic. All right, until we sit there and we force our third postulate to include Einstein's second postulate, which was what? What was the second one? They stated.
Light moves at the same speed.
Yep, light moves at the same speed. So in other words, we can say that at all times, our third one, x prime is equal to ct prime, and that x is equal to ct. In the event object that we're dealing with is light, this has to be true. Now that's going to change the ballgame. Okay. So, if we plug these two equations into our x and our x prime, and we solve that, we will find that capital C is equal to negative b over c squared times a. You will find when you do this, I should say. I don't know a really good way to denote big C and little c, so I always just write C bigger. Just ask me if you're not sure what I'm talking about. Negative sign.
And is the v squared or the c squared?
You know, you can pick whichever's convenient. All sorts of problems. Yes, the c squared. Which makes this a lot smaller. Obviously, anytime you deal with c squared, it's going to be a tiny, tiny number. So, let's figure out what we've got. If that's the case, here's our third criteria. We now have variables for everything. What do we end up with? Well, all right, so we started off with our x prime is equal to ax plus bt. So now I can say that my b is negative av. So my a can come out. I can say that x prime is going to be equal to ax minus bt. That was easy. Now if we look over here, the only difference between this and the original is now we're multiplying by some sort of factor a, which granted we don't have information about that just yet. Alright, so what else do we know? Alright, let's do the other one. We've got t prime is equal to cx plus dt. Now c, I've got minus v over c squared a. That's ugly. So t prime ends up, the only thing we can pull out is the a, so we end up with minus v over c squared times x plus straight up t. It would have been 18. Since our d variable is just equal to a. So slightly uglier. That one's a little bit different, especially since t prime is just equal to t before. Okay, now these are x prime and t prime in terms of x and t. Now you can solve these the other direction. You have to solve these in the other direction. The answer becomes x is equal to 1 over a times 1 minus b squared over c squared x prime plus t prime, and t is equal to 1 over a minus b squared over c squared times plus b over c squared x plus t. Okay, those are the same equations. There's nothing spectacular about them except we solve the other variable. Now, here's what I don't get. Now, in this equation, y isn't, so let's multiply through here for a second on our x prime. We've got ax minus avt, right? So if we wanted to put this in terms of x, why can't we just add avt here and then divide everything by a? Shouldn't that be, why did this get so much more complicated? If we're saying that's the same equations, I'm telling you that looks a whole lot more complicated. Where did this v squared and c squared even come from if we just solved that equation for x? Somebody's got to give me that answer.
Read the doubles, weird way to square both sides somewhere.
Well, great, but where the heck does the v squared over c squared come from with x? Come on, you guys can do this. Find it. Can't find it? It looks like you should just be able to switch it around.
I'm just gonna make that with those guys.
Time is no longer than
Ah, okay. Thank you. See? Told you we could.
too busy copying down.
I know. The x prime equation, and it's always going to be like this, is a function of x and t. So when we go to x, we need to do this as a function of x and t prime. We have to switch out the t's. Because we're always going to say, okay, I know everything about that coordinate system. Give me some knowledge about this one. So the bitch of it is, you've got to use this for the t prime when you put it back in, and that's where we end up getting the v over c squared. I am still writing that, right, aren't I? No, I'm just making shit up as I go, aren't I?
Isn't that what one was about?
Why are you kidding me? Let me make sure I'm writing that down. No, okay, I did. I copied it down right this time. Just wanted to make sure.
So everything on the board is correct.
Yeah, everything on the board should be correct. Well, whenever I'm taking notes, I you guys probably find this too, my mind can move faster than my hand. So then I just kind of start daydreaming or thinking about the next thing that I want to do or talk about. And who knows if my hand writes down. All right, so. Yeah. Now we got a slight problem, though.
Is that a W or V up there?
What'd you say?
Is that a W or a V?
There's no W's, so the answer is V or something else.
So is that a positive? Is that a plus V?
This is a plus V.
Okay.
Now, the reason the book's written it like this, and I do kind of like this is unique to the book. The idea being is that mx plus b relationship, it's always trying to phrase it that way. So we're showing here that this is a plus v over c squared, whereas over here it's a minus v over c squared. Because normally whenever you have the minus, you write the other way around, t minus something. But we want the x coordinate always here first, and then this is the constant. So that's the way it's written. I kind of like it, actually. Unique to this book. Okay, so. Now, has everyone got these written down? I'm just going to write these two over here. You can solve the other two. For the other two. X prime is equal to just a x minus t. That is a t prime is equal to. Alright. Now we have our special relativity transformation set of coordinates. I'm going to erase all but two of these.
So with those just two equations you just read up, put in there, we get both of those. That's what
Okay, start that over. So
with those two,
you
we get
these two, right. There's nothing you need to go from those two to get to these two other than just moving around within it itself. Okay, solve for those variables. It's ugly, it's a little bit of algebra. I mean, that's probably the longest part of your homework is just moving those around to solve these. Okay. Now, I'm going to erase this time one. Alright, so when we created this with the idea that one coordinate system was moving with respect to the other. We labeled one s prime and one s. Now, whether one coordinate system is moving one direction or the other is moving the other direction, it doesn't matter. One is moving with respect to the other. Okay, that's all we really care about. So the point being is that we've created these coordinate systems with this x prime, s prime, but if we were to start all over and label the other one as s and the other one as s prime, they should be the same. Right? It was completely arbitrary how we set this up. This is a problem. In other words, if we switched all these, I should be able to switch all the primes on this one and all the values on this and have it still be the same thing. Okay? We know that with one exception. What is the one exception?
with time.
Not time. My phrase is better. Read it.
I'm not sure. I was going to say maybe light, so it's like instead.
It's not like, I don't expect you, that was an absolute shit way to ask that question. We've set positive axis in this direction, right? This one we know is moving with a velocity in this direction from this one, or this one is moving with a velocity negative with respect to this. So there's going to be one negative sign difference. In other words, if we just look at these transformation equations, I can erase this over here. I've written it down such that x prime is equal to x minus vt. If I solve this for x, I have a crazy equation plus vt. The only difference is the positive sign because of how we set up our coordinate systems. This still has to be true over here. It has to be because based on symmetry, whichever one we start with, the opposite has to be true other than that vt. So here's the thing. We have this x equals x prime plus vt. Okay, and we've got that same thing over here. Okay, so if those things we switch around and we're absolutely fine. That's going on. So what does that tell us about this and this?
That they're equal?
They have to be equal. The only way this can possibly work is if those are equal. Otherwise, we can run around and switch all of our primes and nothing makes any sense. This is the other big, are you with me? Because you have to buy into this for anything.
So go over that again.
Wait, find a what?
That those two values have to be equal. Okay. Now, the idea being is that we started this off with the arbitrary s prime and x. Now, we could go back and I'm going to go over here and do the crazy thing, and I'm going to call this s prime like that. All I'm doing is moving the prime. We should be able to go around and just move all the primes and end up with the same variables, with the exception of we're going to end up with the minus bt or plus bt, because one's moving with respect to the other. That's exactly what we had here, but we solved one for the other. I could run around and just switch all the primes and the equations would work. They have to work because I could have just called the other variables the opposite thing. I could have labeled my first coordinate system as s prime, the other one as s. Okay, the same thing has to be true over here. There's nothing special about this. I should be able to go through and label all my x's as x prime and my x primes as x. Now, we're already set up to do that with this x minus bt and this x plus bt, just like we originally were, if one thing is true, that this whole giant coefficient is equal to a. Now, if you don't believe me, then go ahead and practice switching the coordinate system s prime and s and solve it through the exact way we already did. And you'll find that you get the exact opposite equation where this big ugly thing is over here and the a is over here. Okay.
We're good. We got to.
But ask a question if you got one. This is probably the crux of today's lecture, is buying into this.
And homework.
Well, actually no, I'm just going to show you the results of this one. We're done with homework. We've already gone through past 1. We're moving towards 2 and 3. Now, in homework problem 4 isn't particularly a problem. It's just practice of everything we did over today. And I want you guys to please at least read that one by Thursday, so that I can assume that you've gone through that.
So we're not actually writing out the 4?
No, 4 is not. 4 is just, I want to know that you guys have all covered that before Thursday.
Okay.
How is a equal 1 over a times something?
Okay, so it's pretty ugly, right? So let's figure out where it's going to go. You're on to the next part of even if it is true, how is it true? And I'm fine with that. So if that is the case, and this is really, really bizarre, we're saying that a is equal to 1 over a times 1 minus b squared over c squared. Come on to the next page. Okay. The easier way to think about this is no matter how we set this up, and I should have done this, I did this better in my notes, is that at the end of the day, the same thing we had before, is that x prime has to equal stuff times x minus bt, and x has to equal stuff of x prime plus bt, right? And the only way that this can be true is if stuff equals stuff. Based on symmetry. If you're to solve the problem the other way, you need to be able to get the same results.
Oh, I was crazy.
Yeah, that's what I have in my notes too. Oh, yeah, it's simplified. A much simpler way to explain this. Okay. So, that doesn't help answer the question as Brad asked. What do you mean? How is A equal to something 1 over A? Well, how do I get A all on one side? Multiply both sides by A, right? If I multiply both sides by A, I'm going to get A squared here, and this is going to go away. So, the beauty of this is I've now solved what the heck A is equal to. A is equal to 1 over the square root of 1 minus B squared over C squared.
Okay, wait, I got a question now.
Yeah.
Wait, no, never mind. You need a question of proof.
I have a what?
So, never mind, you need a question of proof.
The question and proof.
Like, as in, you did that step and question more.
Gotcha. Well, that's good to hear.
Because it's a square part of an out, and I was like, wait, doesn't that mean it's not linear now?
No, that's just a coefficient. That's going to be a single value. Think about what is it? Those are all constants. V is the speed at which, no, it's a good question though. It wants to know, does this violate our idea that everything's linear? V is the speed no. V is the speed that one origin is moving with respect to the other. Now, if we go over to here, our rule number 3, I guess as I have it, 1, 2, 3, or no, rule 2, I guess there's only 3. Frames also move at a constant velocity with respect to each other. Has to, for any of this to work, which means that this is a constant value, speed of light's constant, because it's just one constant based on wherever the speed is between. Okay, so doesn't violate it. And we just get some version where it's kind of shifted. Okay, so this is such a big thing in relativity, it gets its own variable. We will define this as gamma v. Besides, it's a heck of a lot easier to write out than I was writing out that obnoxious thing. So we can now rewrite our equation much, much simpler. We say that x prime is equal to gamma v times x minus vt, and x is equal to gamma v x prime plus x prime. We've satisfied our linearity. We've satisfied the fact that if you just switch the primes, everything will work out just fine, except for the negative sign of the velocity. And we can go home. We're happy.
Go home.
Well, not home. We can go back to being worthy. So, same thing is true with our time component. We can now throw this back in there, which makes this easier. Now remember, the sign switch is always on the V. That's the reason that the book writes this as plus V minus V plus V minus V. It's at the second part, so this isn't going to be minus T or plus T. It's specifically on the V. If that negative sign switches back and forth. Neat. Okay, so now let's take a look at this gamma V for a second. This gamma V variable. What can I say about it? In the gamma V variable, now when our speed of, the speed of that the origins are traveling with respect to each other, v, when that goes up. All right, so one origin is traveling much, much faster than the other. The other one's standing still is usually their assumption. Is gamma v go up or down? We're trying to set some limits on gamma and understand where it goes. So let's say that v is very large. The speed with the second origin moving with respect to the first one is moving quite quickly. What does that tell me about my gamma? Big, little, negative, positive? Okay. The larger the velocity is, the smaller gamma is. Well, yes, no. You're saying yes, he's saying no.
Larger the larger velocity is.
What do you mean you don't know? There's one little equation.
Oh,
So the larger, faster the speed, the higher the gamma.
Faster the speed, higher the gamma. Jared has gone on a limb and shouted above the crowd saying, faster the V, larger the gamma. Do we agree? Drew, you had a question.
no.
That was not his question. I doubt anyway.
Using that, so V in that equation, right, goes to?
Yeah.
So V goes towards infinity.
Larger being smaller.
I guess my question is C, the speed of light.
Okay, so we're making some assumptions here. So Drew said on a point. The assumption is that we can't move faster than the speed of light. Nothing moves faster than the speed of light, which we're going to understand here in a little while, hopefully. The point being is that the maximum V can be is the speed of light.
Well, I mean, just below it, because it could theoretically be the same.
No, we can use this for talking about light. So we can actually use it when V gets to C. But in any case, it can't go over that. So with that limit in mind, we agree with Jared's idea. If V goes up, does gamma go up?
I'm going to say larger than V and smaller gamma.
Okay, we got 2 against 1. This is basic algebra, guys, and you are wrong, sir. They're right. Look at this. All right. So let's take the limit. The limit is if V squared is equal to C squared. And that's true, we c squared over c squared, we get 1. We get 1 minus 1, we get 0. 1 over 0. Okay, that's slightly confusing because, you know, only Chuck Norris can do that. So, we go back here and we say that v is slightly less than 1. If we square that, we've got 1 minus almost 1, right? And this becomes a stupid tiny number, okay? A really, really tiny number. 1 divided by a stupid tiny number is actually a really friggin' big number, okay? So gamma v goes up. Now, what happens when v is really small? I'm sorry, no. What happens when v is really small? Speed of the origin. So like I'm sitting here moving here, here's my origin, this is mine, and my grandmother walking with her walker is the other origin. If that be the case, what is the gamma factor between us here? Small. How small? Like 0.00001?
So you're almost divided by 1, so it's almost.
So what's the limit? Yeah, that's my point. If you're almost, he's got the right idea. We're almost divided by 1. So what is the lower limit of gamma? 1. Yes. You just don't, you want to speak up. You're afraid to be wrong. Don't worry about it. You can do this. All right. Yes, the lower limit is 1. Because if this goes down to 0, we have 1 minus nothing. Square root of 1 is 1. 1 divided by 1 is still 1. We got 1s all over the place. If that's the case, then the very lowest we could be is 1. In other words, my frame of reference is a 1-to-1 ratio essentially to grandma's as she goes up. Now the other limit is it could go off to infinity. It could get very, very high if I start to get to values that are here. So gamma v necessarily is greater than or equal to 1. How far off of 1 determines how much relativistic effects we have. Let's give this a shot in the dark, and this is actually one of your homework assignments, I think 3. Let's just say, let's take something fast. What's the speed of sound?
Roughly 3 times.
343 meters per
Meters per
second.
second.
There you go. So let's go through about 340, just to make that easy. As far, in terms of planes that fly that fast, which is about 700 miles per hour, what do they say that they're doing?
Mach speed.
Mach what?
1, 2,
Mach 1. What is Mach 2?
2 times the speed.
2 times the speed of light. That's how the Mach scale works. So, what is the fastest planes that we usually deal with on Earth? That we aren't spacecraft that are taking off?
Is it 3 or 4?
Mach 3.5, something like that. So, as far as here on Earth, let's deal with Mach 3. That is really, really flipping fast. Well, let's say that's about 1,000 meters per second. Okay? That work? 1,000 meters per second. Give me the gamma value. Somebody run this on a calculator. What the gamma is for, you know, our supersonic plane that's moving at Mach 3. Yeah, we got it. Oh, sorry. So you're fine.
It's in the 9th.
8. 3E8. Anybody drink tea in here? Or is that just, you know,
Like sweet tea.
old? Is that just something we had?
Are you Dr. Nacker now?
What'd you say?
You Dr. Nacker?
Yeah, well, apparently I'm becoming him slowly. No, I was just going to say, so I do like tea, but this tea's become really bitter because I left the bag in there. I think all of you guys know Audrey Smith,
Yes.
aside from me for the companies. Whenever she makes tea, she just leaves her tea bags in the thing and just drinks it with the tea bag always in there. I don't know how she does it. I mean, it's like drinking battery acid after a while.
1.
I haven't personally had that experience. It's
You
just
got
like-
exactly 1.
Well, no, it's like 1.0, like 10 zeros and 1.
Okay, to the point that basically your calculator, we're basically almost reaching the ability of the calculator to come up with anything. So even at Mach 3, we're at 0.01. 0.000000001. Okay, so we have to be moving awfully fast to see any relativistic effects. Even these planes moving at Mach 3 are completely oblivious to relativistic effects. Okay.
And wait, Mach 3 is like a fraction, like, how small a fraction is that of?
It's 2,000 miles per hour, so it's moving. But
Yeah, but not compared to speed of light.
not compared to speed of light. Well, it's 1,000 over 3 times 10 to the 8. So you can do the math. 1 times 10 to the third over 3 times 10 to the 8th. A lot of zeros here. Okay, so.
So what's the units for gamma?
Good question. What are the units for gamma?
Make that big one.
Well, we need to know anyways.
Not yet.
Okay, why doesn't it have units?
I mean, just looking at the equation, it's velocity divided by velocity.
Exactly. It is a unitless thing.
It's like a ratio distortion, right?
Yeah, exactly. A ratio distortion of your velocities compared to the speed of light. And that's what relativity is the ratio of your velocity with respect to speed of light. How fast are you going? Okay, so now that we have all these equations, I'm going to erase these and I can now write them as gammas, because I now have that. So I've got x prime is equal to gamma v times x minus vt.
Bless you.
Thank
Bless you.
Yeah, we're no well. We had the long weekend. I was talking to Brad about it. I said, man, we had class yesterday. Well, we would have. Doing a little bit better though. Okay. All in terms of gamma v. There's a gamma v. Now we put gamma v. The reason being is gamma. The only thing that varies in is the velocity of the origin, the difference between the origin of the systems. So that's why it's gamma subscript v. All right. So. Now, when is this useful? Well, let's go back to talk about Anna and Bob. If we want to talk about the time difference, we're saying that Anna sees something and it takes, 10 seconds. How long does it take for Bob to see it? Something like that. Or we're saying that Anna sees something as being 3 meters long and Bob wants to believe that it's 6 meters long. Well, how do we go about solving that? Well, what we can do is we can say if Anna sees something at a certain length, that length is going to be measured about between the two ends, x2 minus x1. Okay, from Bob's point of view, of course, it's going to be x2 minus x1. And these are not necessarily the same thing. Okay, so let's go ahead and assume that Bob has stated to Anna that she caught a fish that was this big. So we know all the information about Bob and this fish.
Continue.
It's quite the chain of sneezes thing. We have very rough, comfortable paper towel up there.
Thank you.
All right. If that's the case, if I know everything about Bob, I know all of his positions, all of his times, and I need to be able to come up with a time coordinate, then I have to convert. So x2 prime is going to equal to gamma v times x2 minus v times 2. Now here's the important part. It matters from Bob's point of view when this happened in his coordinate system. So we have to do this for both of them. x1 prime, gamma v, x1 minus v t1. And we can solve both of those and we figure out what x2 minus x1 is. The neat thing about it is if I do that, if I now write out x2 prime minus x1 prime, it's going to be equal to, and if I multiply all this ugly crap out, I'm going to have gamma v x2 minus gamma v vt2, that's supposed to be equal sign, plus gamma v, oh no, minus, because I'm subtracting them, x1 plus gamma v times t1. It's this big long mess. So if I then smash all this stuff back together, x2 prime, and you don't have to write it down if you don't want to, is going to be equal to gamma v times x2 minus x1 minus v times t2 minus t1. It's really handy. Instead of going through this mess, you can actually just put in the change that you're interested in. From her point of view, I want to know how long this is. Well, from his point of view, how long was it? And then how long did it take for whatever he was doing the measuring? Okay.
Is that V subscript 1 on the second tone, or the second to last question?
It was smudging the board.
Oh, okay.
Did you smudge?
I'm lost. Here, somewhere?
It's
Move
good.
over a little bit to the left.
Left,
Go,
left,
go.
left.
There we go.
Oh, this is a,
Yeah.
yeah, that's a bad board. There's actually no blackboard there.
Oh.
Yeah, it's giant hole.
it'd be funny if I did it, and you thought it was
So, I mean, are you sick, allergies, or you just allergic to Jerry?
I don't know.
I thought everyone was.
I just have season disorder.
You have what?
I see the
Season
random
disorder.
things. He thinks it funny. So whenever I tweeze my eyebrows, I sneeze like crazy, and he thinks that's hilarious.
Well, I think I've got a different example. It's,
So like, it's like us shaving, if we start shaving and we start sneezing all of a sudden, would you think that's funny?
it'd be really awkward, that's for sure.
Yeah, how would you actually shave that thing yourself?
Yeah, it would be really tough. Okay, oh, we lost Brad. All right, so if we summarize this, this is what she sees, what he sees, and then also how long. The time interval that he sees. And we can do it the other way around as well, using the other version of equations. But it's nice that we can just take these values as a quantity. All right, so now let's solve an example problem.
Time interval what?
So time interval that he specifically sees. And you got to keep that. You got to keep track of that. So it gets very, very important to copy down correctly your prime coordinates, because where those are define everything else. All right. So example 2.1. Alright, so our good friend Anna is back. She's holding her lights like this.
Get her voice back.
Oh yeah. But Bob doesn't really care because he's already seen all the leaked pictures of her on the internet, so it's not really that exciting anymore.
Just like, did we not think this through the slightest?
What? Wait, what?
It went up to the cloud, no one understands the cloud.
There's an interesting story online actually about all the pictures that have been released that they weren't found that way, and that it's actually a clever ploy by Samsung or something like that to release this the week before the iPhone came out and blame it on the cloud, which I think it sounds like a ridiculous scandal theory. But the one thing that is interesting is the fact that anytime pictures are released before, nobody's ever said how they got them. So the one thing that does kind of make sense about the story is, why would this person not only say where they got them, but also tell the manufacturers how he did it, or not how he did it, but that he did do it, so that they can shut down that loop so he no longer has access to it.
Well, wait,
Whose phone is that?
Mine.
that's a great hat for you.
I mean, some people need that kind of attention to know how they managed to do it.
Yeah, but they didn't go into details of it. It just seems interesting that they would have kept that exploit open. The other thing is, the person who did this didn't try to get any money for any of this, just threw it all out there.
I mean, so who would just pay attention that badly?
Could be. So the argument is that whoever did find this, that it was some hacker that was specifically paid by Apple to make Apple look bad. That was the article. Like,
I mean, they've even named the event.
Wait, are you talking about the?
Yeah, no, please.
Okay, yeah.
Well, yeah, but it was her and 12.
Yeah, there's a bunch of other ones.
There's a lot more than that.
Oh,
I
yeah.
like your
A
voice.
large.
No, if you want to see a whole lot of Verlander junk, there's
Oh, okay.
Kate Upton's, Kate Upton, all of her photos and everyone else. So, everybody's knows.
That happens.
All right. So, back to physics. Bob's watching Anna again. He's just not as happy. So, from Anna's point of view, she's got these two flashes that go off. Remember we talked about this before. What was the conclusion that we said from Bob's point of view?
One happened before the other.
One happened before the other. Do you remember which one?
One on the left.
Yeah, one happened first. So now we're actually going to get numbers. Now that we've got our equations, we have our transformation equations. We're going to try to get real numbers to this. All right, so from Anna's point of view, we have right here, we have this distance being 2 meters.
You want to turn the camera a little bit?
Oh, fine.
Just in case.
Just in case.
Yeah.
There we go. All right, so off Anna goes 2 meters apart. So the question becomes, we want to know how far does Bob see this? Now, how fast is she moving? In her hoverboard, she's moving at 0.6 times the speed of light. She's moving. She is definitely moving. Okay, so from x2 prime minus x1 prime, we can say that this is equal to 2 meters. Now, what about the time change? Oops. From her point of view? What is the time change from her point of view? Time change from her point of view from these light flashes. 2 meters apart.
Oh, 0.
0. One point is she sets them off at the same time, and it's Bob that sees them at a different time. So we can say T2 minus T1 is equal to 0 seconds. Alright, so now the goal is, with this knowledge, is to figure out what T2 minus T1 is. How does he see these as a different time difference?
Hey, about a second.
Okay, congratulations, you can read the book. Okay. To do this, we have to use the conservation rate. Okay, so this. T2 minus T1 is equal to this gamma B times plus V over C squared x2 prime minus x1 prime plus T2 prime minus T1 prime. Now, right off the bat, we already said that this is equal to 0. She sees no time difference between them. That's handy. So we can see that the delta time, as far as Bob is concerned, change in time unprimed is just going to be gamma B times V over C squared times 2 meters. Okay, so now she is moving. Let's calculate gamma V first. Gamma V, again, is going to be 1 over the square root of 1 minus B squared over C squared for 0.6. Run this on your calculator and see what you get.
1.25.
Did you actually do this, or are you still just reading out of the book?
Well, my student just wanted the number.
That's actually what somebody calculated. You're being oh so helpful here. Yes, 1 1/4. No more comments from you in your book, please. Thank you.
So, what's
Otherwise, you don't have to come to class. There's no test policy here. You just stay home and read the whole book. It's fun by me. Come take tests.
You want us to use 3 times 10 to the 8 or 2.98 times?
3 E8 for all calculation. Yeah, it'll be a pain. I still think that's fascinating how remarkably close it is to
I just don't.
3 times 10 to the 8th.
So I got 1.8 times.
I just want to make sure that we do get the 1.25. Did you get that or no?
Oh.
Good practice. Anybody verify the 1.25? I forgot to get that inspired now. You didn't get that halfway through last year?
Yeah.
I like them.
Good, except for basic graphing. It's terribly hard to figure out on here. Creating lists.
So you're not getting it? Now, are you squaring
No, I
this?
didn't do it right.
Oh.
Okay, now I'm going to teach you guys a trick whenever you're calculating these, because we're going to end up with these fractions of V over C all the time. There we just got 1 V over C. It's given to us as 0.6, right? 0.6 C. So don't even worry about the C. There's no reason you even need C. It's 0.6 C. So the way that you can write this is going to be equal to,
Wait, why are we using 0.6C?
because we said that's the velocity she's going right
You
here.
don't need the C anymore.
Yeah, you no longer need C in any of your calculations, so it's really handy to just do 1 minus 0.6 squared. That's all that this is.
Yes, you got 1.25.
Good, 1.25. Yeah. All right, 1.25. Now, this is moving 6/10 the speed of light. if obviously moving the speed of light is the maximum we can get to. We're talking about gamma being this number that is greater than or equal to 1, already at 60% the way there, we're up to 1 1/4. Gamma doesn't vary all that much, okay? You have to seriously be going 0.9999 times the speed of light to make this number anything sizable. But nevertheless, we can say that this is 25% over classical physics, so we will see some relativistic effects, although they might not be that large. All right, so then we plug that into this equation. So again, unfortunately, we do have to use C here because we're going to end up with 0.6 divided by 3EH is the way you can enter this because one of the C's cancel. So that's nice and convenient. And we do get an answer here of 5 nanoseconds. And we're going to run out of time. Crap. Okay. The point being is with this delta T, with the 5 nanoseconds, is that that's the time difference between them. Yes, sir.
Okay, so whatever's after that 1 is a percentage that's bigger than it's over classical mechanics?
Yes, and I shouldn't use percentage. Think of it as the general concept of how much relativistic effects are going to matter with the 0.25. We still have the B over C squared here, too.
Okay.
Gamma is just a good idea is to say how relativistic is this system. Okay, and anything that's over 0.1 we'll consider definitely relativistic.
So say if it's under 0.1, we may just use classical mechanics.
For the most part, yeah, you're going to be pretty solid. All right, 5 nanoseconds. But the point I want to talk about here is because we do have to talk about one quick thing so you can get your homework done. T2. Now, we set these events up as, I forget, yeah. This one happens first from Bob's point of view as it comes by. This one happens the second. So if we had actually solved this, we would have found T2 as negative 2.5 nanoseconds and T1 as plus 2.5 nanoseconds. In other words, instead of doing the difference as we did, if we just plugged it straight into the equation, we've got an answer of minus 2.5 up here. Which is to say, but
Shouldn't the T1 have a negative on it?
no, because it's the further west one that is negative. What that means is that from Bob's point of view, this flash went off before the origins crossed. This one went off earlier, 2.5 seconds before the origins even crossed. This one went off 2.5 seconds after the origins crossed.
See what the math now is.
Right. Okay, so last concept, time dilation. So there's 2 special cases that I want to talk about really quickly, like within 2 minutes apparently. The first one's time dilation. Let's say, for example, we've got okay, our person, this becomes a very simplified person, is on a cart moving like this. They're holding a clock. Go with it. Then, sometime later, the same person is standing there holding their clock, and time has changed over to there. That's what the clock looks like. Bob is just watching it from this point of view. Okay, so now the important thing with this is that from this, the S prime coordinate system, the one that's moving with respect to this, what is the position change of these 2 events? We'll call this event 1 and this event 2. In their coordinate system, what is the position change of the clock?
Opposite?
None. That's got it. It's none. They're holding a clock. They just happen to be moving this way. There's only a position change from their point of view. The point being is that x2 prime minus x1 prime is equal to 0. There is no change there, but there is a certain amount of time that changed. So if we go up there and we look at our equations, if I want to figure out what the T2 minus T1 change is, I'm going to say that this is going to be equal to our gamma V, and then the x change, the x position change that I'm going to see, is going to be equal to 0. This whole thing is going to fall out. Now this is the prime coordinate. I don't have the other one written up here right now. So this is going to be 0 plus the T2 prime minus T1 prime. All of this is going to be 0 because there's no time change there. So this just boils down to that the change in time from this coordinate system is equal to gamma V times the change in the prime coordinate system. Change in T0. And this is what is known as time dilation. Now, why did I write this as T0? The reason being is that we want to say the change in time with respect to any moving coordinate system is equal to gamma v times the change of time in the rest coordinate system. And we'll put this as 0. The problem is that we could have said that S was moving or S prime. We don't know. Because in this case, it could have been Bob that was holding the clock that was steady, and then she was moving with respect to it. The point being is that wherever the clock is not moving, so in the reference frame where it's not moving, which in this case was Anna's, that's where the 0 is represented as. Does that make sense? So this delta t, we can measure this from Bob or Anna's, it doesn't matter, relative to where it's not moving, and that's in hers. Now the other one that we want to do, and I guess I'll just leave as a reading assignment, is length dilation. It's the same idea. If we take the example, thank you. Okay, if we take the idea that we're saying from Bob's point of view, when he was measuring her plane and said that it would fit in the hangar, like this, he was saying that he measured the front and the back at the exact same time. You had Bob Jr. measuring back here, Bob measuring up here. So the length of time from this point of view was 0. If that's the case and you work out the math, you're going to end up with the change of x is equal to the change of x of 0 over gamma v. This is known as length contraction. It's just a simplified version of these formulas that is useful if you take a measurement of the time. We'll pick up with that, but you're going to need to read that section. It's a whole paragraph and a half. Where is it? 18 and 19. Yeah. Okay, so you're going to have to finish. We just went through example 2.1, so read the bottom of 17 and 18, and then you need to read 2.2. And that's going to help you answer your question 2.
On modern physical.
You're a modern physical.
Modern.
You're what?
Modern.
Modern. Wow, yeah. There's no M. Look at that. Yep, modern physics. All right, guys.
There's a class there.
What'd you say?
Got that 50 class today.
What's that?
Modern.
Oh, modern.